So now if you see this HCM version, okay, in the same itself we will be trying to implement. So let us take some two datas. So I'll take move, say some R not register. We are transferring a data called as 05H, okay, and one more data we'll try to store in R1 register like 07H, okay, or I'll make it as E, right. So now let us see how it is being updated. Sample. Yeah. So your R0 is loaded with 5 and accumulator is loaded with 7. Okay. So now we will check the single operations. Update the frequency. Okay. Now let us add the two contents. Add A, comma R0, R0. So now run the program. So now see the value has been executed. So if you want to see uh, single wise, so I'll use stepwise. I'll reset this. For 1K, the ideal case. So first assemble, okay, then so R0 is loaded with 5, then A is loaded with 7. So what is 5 plus 7? So 5 plus 7 is 12 in decimal, whereas in hexadecimal it is not so. In hexadecimal 12 is known to be C. Okay, means in hexadecimal format, so we have the numbers like 0 to 9. Okay, and from 10 onwards we consider them as A, B, C, D, E, F. So let me just write here only. Let's reset that. So I hope you everyone are aware of number system. So if you take your hexadecimal number format, okay, so it will be right 0 to 9, okay, and then A, B, C, D, E, and F. So this will be the number system. If you take the decimal format, so it will be from 0 to 9. Okay. Now from 10 onwards, okay, so your decimal value will have two place values. But for hexadecimal number, the maximum number is 15, right? So that will be given in terms of, okay. So A will be 10, B will be 11, C will be 12, and D will be 13, and E will be 14, and F will be 50. So this is how we have the numbers. Okay, so number representation in your hexadecimal. Now when you add 5 plus 7, we will be having the result as 12, that is in decimal, whereas in hexadecimal format this 12 is equivalent to C. So this should be the result what we should get in our uh, accumulator register. Okay, so now let us see whether we are getting that result or not. So stepwise, so R0 is moved to 5, so 5 is moved to R0, then yeah. So A is moved to, so 7 is moved to A, and then your R0 will be added to A, and A will be updated with a new result, that is C. So now you can check here C. Okay, so this is how you can implement the addition operation. Okay, so now we have seen certain representations of addition. So how addition can be performed. So I'll update the frequency by 1. Okay, so now see here at R0. So now there is a big difference between add a comma at r naught. At r naught, in the sense we have a register. So we have a register. We have a register r naught which is having a value called 05. Okay, and a is moved with 07. In the earlier case, we tried to add the contents of a and r naught, whereas now we are using indirect addressing. Okay, where the contents of A will be added to the address at the address which is stored in R0. Means this 05 earlier it was a data, now it became a address. Okay, so in 05 location, 05 location in the sense 1, 2, 3, 4, 5. Okay, so 00, 01, 02, 03, 04, 05 means your R5. Okay, so there we'll load some value, move 05 comma hash 05h comma hash hash say some let us keep it as 10h. Okay, so 10h is so I'll make it as 0ah so that you can aware of it, right? So 05 and we are moving a data called as uh, to 05 location we are moving 0ah. Now let us assemble this. Okay, so it is free from error. So now what we do, we write it stepwise. So R0 is loaded with the 5. Okay, so now 05 location. Okay, so if you see here 05 location is loaded with 0a, and corresponding to 05 it is the register bank R5 of your register bank 0. So that's why your R5 will have a value here 0a. Okay, so now this what we are doing in A, we are moving 7. Okay, so once we move 7, then we have to add the contents. Now in the earlier case, the contents of R0 is added with A register. Now here it is not so. The contents of A will be added to the address which is holded by to the contents of the address which is holded by R0 register. So R0 is holding an address called as 05. Okay, and in 05 we have 0A. Okay, so now 0A will get added with the 07 and A will be updated. Now let us see. Now see here, it has been added. Okay, so now 0a plus 05, how much it is? So 0a plus 05, 0a is 10. Okay, 05 is normal 5, so 10 plus 5 we will get it as 15. Sorry, we are adding 7, right? Okay, so 7 plus 10 we will get it as 17. Okay, in decimal, whereas here we have a result as 1 1. Okay, so what is 1 1? Why we got it as 1 1? Anyone?
Yes, sir, because after F, the next number is 10. That is
Okay,
equivalent to the decimal number of 16.
yes.
And then the next number 17 is also 1 1.
Yeah. So see, after in your hexadecimal number representation, okay, your 15 is known to be is given as F. Okay. After F, the number will count starting counting from 10. So 10 represents your 16, 11 represents your 70. Okay. So when we add 7 and 8, that is 7 and 10, it is 17, right? So 17 in decimal, whereas in hexadecimal it is 1 1. Okay, so now I hope you understood the difference between your adding the contents, okay, and adding the contents with respect to the address locations. Now we'll try to implement one new thing. So since we have completed that these four sections, now I'll add B, comma, let us say I'll add straight data 05h. Now let us see whether this will work or not. So anyhow, you understood this 4, so that's why directly I'm going to run the program. Okay, so now see here, we got a syntax error, okay, stating that b comma hash 05. So why? Because, okay, so for performing an addition operation, straight away you can't take a value called a register called b. Only a has to be used. Okay, so that was the error. So now what I will do to this a means to this 11, okay, 11h, we are adding 05 again, or I'll add 03h. Okay, and let us see how the value is updated in your a register. It should be 14, isn't it? So let us see whether we are getting 14 or not. Yeah. So you got accumulated as 14, isn't it? So this is how your addition operations can be performed, right? Now let us replace this the same thing. I'll replace this with subtraction sudd. Okay, so let us start with the normal thing. So I'll make this as comment. Just deleting this. So first we'll see with R naught. So the contents of R naught is subtracted from A. So just to add some complexity for better understanding, so I'm putting some reverse the numbers. Now see, it is A minus R. Okay. So 7 is larger number and 5 is the smallest number, and let us see how the result will be. First, let us assume, let us estimate how the result will be. A larger number subtracted from a smaller number in your digital electronics. What will be the number format? Any student can tell. The question is open now. Please. So what will be the subtraction of 5 minus 7? So I'll put it in chat box also. 0.5 minus 0.7 will be how much? So everyone will tell that it is minus 2. But in digital representation, what will be the answer? Yes, students, anyone can just come up with the answer.
Sir, it will be
Yeah.
FE.
Yes.
FE.
FE. Okay.
Yes.
So how you got that? Why
So
it
just
should be minus 2, right?
yes, sir. 5 minus 7.
Yeah. It is minus
Yeah,
2.
sir. Yes, sir. Minus 2. Actually, sir, just I have subtracted bit by bit operation.
Okay. Fine. Right. Okay. So actually, what is the thing is, your minus 2 is represented in its 2's complement. Okay. So in your digital electronics, the data, whenever you give a negative number, the storage will be done with respect to the its 2's representation. Why? Because minus represents just a sign. Okay. So now let us see whether we are getting FE or not here. Okay. So we'll assemble that. So one by one only we'll be doing it. Okay. So run stepwise. Okay. So R naught is loaded with 7, then A is loaded with 5, Okay, then see FE. Okay, and something peculiar you might have observed here, your PSW. Okay, so your PSW, if you see, it is 11000001. Okay, so now here we can see how the data has been checked here. Okay, so let us say, so can anyone remember how the PSW of 8051 will look like? Anyone? Or shall we again revise it? So if we see the PSW, okay, so for this I'll just use some Word document. Okay, anyone can interpret that 8051?
Yes, sir.
Yeah.
Sir, if we talk from the MSB, uh,
Okay.
then that is the first one is the carry flag.
Right.
Then sir auxiliary carry.
Right.
Then sir flag bit 0, which is for general purpose user flag.
Okay.
The next two is the register bank set RS0 and RS1.
Okay. Very nice.
Then sir overflow flag.
Okay.
The second one is not used generally, and the first one is the parity flag.
Okay. So exactly. So now I'll just show you exactly how it is decoded. Okay. Um, Now see here, so this is your PSW. Okay, so now whenever we are trying to subtract 05 minus 07, so we got a value called as FE, isn't it? So now FE, right? So if we decode into the digital format, it is triple one, sorry, double one double one. Okay, E is double one one zero. Okay, so now if you see the structure of MSB, okay, so MSB bit of any result of any register, okay, or any data, if your MSB is 1, that directly represents the sign number. Okay, so stating that, okay, you got stating that it will be your negative number. Okay, then this sixth bit, okay, so this is your auxiliary bit of your 8051 PSW of 8051. So whenever there is an extra bit that is existing between this MSB, sorry, at the third bit level, okay, we call it as an auxiliary carry. So let me make you some more clear thing. Okay, so I'll make it as sorry, yeah. So I insert. So now this will be your MSB bit, okay, and this will be your LSB, so which starts from 0, so or which is mentioned as 0th bit, and this is mentioned as 7th bit. Okay, so with the help of arithmetic operations, we can elaborate this PSW. Okay, so we know that this this is the 6th bit, 7th bit, sorry, 5th bit, 4, 3, then 2, and 1. So whenever we take your LSB, right? So your PSW. So these two bits are reserved. Okay. So now let us see. LSB bit, we got it as sorry, LSB, and this is your MSB. So whenever in your data your MSB bit is 1, okay, your sign flag will be set to 1. So anyhow we don't have the sign flag, okay, in our PSW of 8051, okay, but whenever your MSB is 1 in your result, it straight away says that it is a negative number, okay. Next, okay, then carry bit. So whenever an operation is being performed, okay, between the two operands and we get an extra bit, okay, at your MSB bit level, right, then your carry flag will be set to 1. Auxiliary carry, whenever we do the operation and during that process at the third bit level, okay, if an extra bit is generated which is propagated to the next fourth bit, then it is said to be an auxiliary carry, okay. And F0 is an flag, a general flag which is reserved, and then RS1 and RS0, okay, are the two flags which are used to select the register bank, and VO OB is known to be the overflow and this is known to be the parity. Now let us understand from this the status, okay. So if you see the PSW status here, it is C1, that is 1100 0001, okay. So let us decode that now. So I'm just putting the data here, so I'll make it as in a different color. So it will be 1 1 0 0 0 0 0 1, okay. So now this is the status what we got from the PSW, okay. So PSW, once we perform this operation, PSW status it is, isn't it? So PSW status we are getting it as MSB to LSB in this fashion, right. Now let us understand from this PSW, okay, from this status of the PSW, what is the nature of this result, okay. So now your MSB is 1, okay, stating that you got and carry, means whenever you are subtracting a larger number from a smaller number, you require a borrow, okay. So for this borrow we had this 07, okay. So actually the operation is performed as 05 plus of minus 07, okay. This is how the operation is performed. It is not just like minus 2, okay. So when it is performed, 05 is 000 and the 5 is 0101, sorry, 0101, okay, and it is added with the 2's complement of 07, okay. So 1's complement of 07, so here I'll write it. So 07, if you take, the actual representation is 0111, okay. The 2's complement is represented as 111 100, okay. This is the 1's complement, and if you get 2's complement, add 1 to that, so 111 1001. So now here we are adding all ones, okay, with 1001. Now let us add these two and see how it is coming. So now see here, so once you add this, how we will be adding? So 1 plus 1 is 0 1 0, 1 is propagated, so it will be 1, okay. Then you have 1, okay. So 1 0 1 0 1 1 1. So now this is how the result is, and this is what we got it also, FE, okay. So when we are performing, okay, so when, let us see now what is the status from your PSW. Now see here, so this is 0 1, okay. So you are getting a carry here, extra bit, so it is called as MSB is being set. At this level also you are having one bit, so you got auxiliary carry as 1, okay. Then F0 RS1 RS0, if the general flag was 0, and RS1 and RS0, since we are working with register bank 0, the status is 00, and overflow will not occur for arithmetic operations, so it will be 0, okay. And the first bit is not used, and you are getting 1 as your parity bit. So parity in the sense the number of ones that are present in this result. So now if you see the number of ones that are present in this result is 7, okay, which is an odd. Okay, so whenever there are odd number of ones in the result, your parity flag is going to be set. If you are having even number of ones, okay, then your parity flag will be set to 0. Okay, so now this is how we need to decode, or we need to understand the nature of the result with the help of status register. Uh, so understood? I hope so. Any doubts in this?
Sir, please can you repeat the even and odd parity, please?
Even and odd. Okay. So, right.
Yeah, yeah,
See,
means when odd parity, odd number of ones are there, that is odd parity. So
what
for odd
parity?
parity, why
Yes.
you set one?
Yeah. See, whenever we have an number of ones in the result, this is your result actually, isn't it? So this is the result what we have updated. So whenever we do the operation, okay, right, and in the operation, once we get the result, in that result, you count the number of ones. Okay, if there are even number of ones, okay, even number of ones in the sense whether it might be number of ones as 0 or number of ones as 2 or 4 or 6 or 8. This is the even numbers, right? So if we have even number of ones, okay, then your LSB of your PSW will be 0. So even number of ones, your parity flag will be reset. Okay. Now if you see our result, okay, that is 05 minus 07, we got the result as double one double one double one one zero. Now count the number of ones: 1 2 3 4 5 6 7. 7 number of ones. 7 is an odd number, right? So you will be having 1. Okay, means whenever the number of ones in the result is even number, then your parity flag is 0. Okay, when the number of ones are odd, okay, your parity flag status will be 1. Okay, means we can say that in other sense, okay, you got an result with even parity. Okay, so where this will be useful? So this will be useful in your communication systems to check the errors. Okay, so whenever we send a bit stream, okay, for intercommunication, digital communication, sometimes zeros may be converted to ones, ones may be converted to zeros. Okay, so the primary check is, okay, so we can see how many number of ones are there, how many number of zeros are there. Okay, so that is why we use this parity flag clearly. Okay, so that's the reason why I skipped that PSW in the theory part, and straight away by taking an example, I'm just quoting over here.
Actually, sir, my confusion is here.
Yeah,
Means when the odd parity, we are setting the parity flag as
we
one.
are not setting. Yeah,
Yeah, means
PSW
the
says
system is setting.
system
Ha,
is going to set.
ha, ha. So, and for the even parity, the parity flag will set to zero.
Yes.
So, sir, actually, why this case happens for even and odd parity? Why the reverse is not happening, sir? Actually, in other cases, sir, if the carry flag exists, then the carry flag will set to one. If carry does not occur, then the carry flag will set to zero. Actually, sir, here we are getting the two conditions.
Yeah.
Actually, even parity, even number of ones, or odd number of ones.
See,
So,
see, see, you are confusing yourself, right? In our
mhm,
example, 05 comma 07, okay, if you see the result, if you see the PSW, the status is 1100 0001. This is
mhm,
your parity flag. So the parity flag is 1, isn't it? Means stating that there are odd number of ones in the result. So that we are checking here. Okay, so we have checked here and we found our result is double one double one. Okay, 1101. So in this result, a odd number of ones are there, isn't it?
mhm,
So that's why your odd parity is being set. For
mhm,
suppose if we got the result, if we might have got a result like this,
mhm.
then what will be the number of ones here? 6.
6.
6 means what is the number, what is the nature of that 6?
Uh,
Even.
Even.
Yeah, so at that time this might be 0.
Mhm.
Okay, for only one
Yes.
result you will not get even parity or odd parity. Okay,
Okay.
based on whatever the result you got. In our example, this is the case. Okay, so for suppose if you add these two, okay, you may get a different value. Suppose say
Yeah.
0.5 if you are adding with 0.7. Okay, so it is 12, right? So 12 means in your digital representation 1100, okay, sorry, 00010010. Now if you see here, how many ones are there when you add?
So two ones are there.
Two ones are there. So two ones means
Yeah.
it is even parity. Then
Even
your
better.
even parity here, it will be status will be loaded as 0.
0.
Okay, so for,
Sir, here is my question.
yeah,
So for even parity, why the microcontroller sets as 0? And for the odd parity, why they set as 1? So actually, this is my question.
why in the sense it is designed like that. Okay, the
Okay.
architecture is designed like that. Okay, if you see the microprocessor, okay, so it is
Mhm.
designed for odd parity.
Okay.
Okay,
For odd
so
parity.
your controllers are designed for odd parity, whereas microprocessors are designed for even parity.
Okay. Okay,
Okay,
sir.
it is
Understood.
not that it is there is some rule or regulation. Okay, so based on the applications, this has been designed. If you go to ARM, right, you have multiple parity options.
Mhm.
Okay, if you go for ARM or DSP process, okay, so there we can identify multiple parities, even parity, odd parities will be there. Okay, so like that, it is designed for that separate application.
Okay, sir. Yeah.
Yeah,
Thank you. Thank you, sir.
fine. Right. So now this is about your subtraction, right? So and the subtraction can be implemented in the same fashion as you have implemented your addition also. So now let us uh, go with multiplication. So how the multiplication has to be implemented. So now for this I'll just use a small number 2 and 5. Okay. So now how the multiplication has to be implemented? Mul AB. Okay, and you have to be very keen that no other register has to be used for this. Okay, only A and B should be the default registers. Okay, and B default sources and default destinations also should be A and B. Now, now if you see here, we are trying to multiply AB, where A is having 5 and B is having 0, because B we have not defined. Now first let us check this result. So 5 into 0, it should be 0. So let us check that value. Okay, then we will add some value, move that some value to B register, and then we will check the multiplication process. Now let us assemble this. So R0 is moved with 0 to, then A is moved to 0 5, and we are performing the multiplication. And now see here, accumulator has become 0 0, because the B value was 0 0. So we'll just add something, move B comma R. Okay, right. Now your R0 value, that is 2, we are moving to a B register so that we can multiply these two. Okay, and the result is 5 into 2 is 10. In the hexadecimal format, it is A. Right? So R0 is moved to 2. Okay, your B register is also loaded with 2, and A is moved to 5, and then we are multiplying the value. Yeah. So now see here, B has been cleared. So earlier B was 2. Okay, now B is being cleared, and your accumulator is being loaded with 0 A. Okay. So now if you see this, okay, so you have A as 0.5, the initial stage, B as 0.2, the result will be stored in A, okay, so which is 0, 0000AH. Okay, so the result will be stored in both A and B, where the lower data. Okay, so your A register, I'll make it as capital A. So A register will have 0A, okay, and your B register will hold this 00. Okay, so this is an 8-bit representation, this is an 8-bit representation. So your result will be 16-bit representation, right? Okay, so now let us implement the same for our uh, division also. So division, so now what should be the division? Suppose say 5. 5 is divided by 2. So once we do the 5 division by 2, your quotient is 2, okay, and remainder is 1. Let us see how the quotient and remainder are stored here. So R naught is 2. So your A is loaded, B is loaded. Now we have to execute here C. Now see here, your accumulator register is 2, that is loaded with your quotient, and remainder is stored with your B register. Okay, so whenever we do your division operation, so this is for multiplication. So when we do the division operation, okay, so your result will have like A register will have the quotient, and your B register will be loaded with remainder, right? So this is we can do. Now we will implement in the same program, we will implement our increment and decrement operations. Okay, so I'll increment A. Okay, so I know the value of A. So A is accumulator was 2. So straight away I will assemble it and I'll run the program and see the accumulator value. It will be 3. Okay, because during the division process the accumulator value was A. Okay, and after incrementing it has become 3. So now we will decrement the value of B also and see. Decrement B. So in the starting stage it was what is that? It was uh, 1. Okay, so now we will decrement B so that it will become 0. Okay, so now see here. Now see your B value has been decremented to 0. Okay, so this is how we can implement your arithmetic instructions. Now what I want from you is, so I'm going to write an expression in the here. Okay, so you need to compile it, you need to execute it, and you need to tell the status of the program PSW. Okay, so using the HSIM or manually whatever you use there. Okay, so is it fine? And is the screen visible now?
Yes, sir.
Yeah. So what I'm doing, I'm going to give an expression for you, just like a small assessment. Okay. So you need to execute this, and you need to tell why this has been, what is the status of the program status. Okay. We don't want anything like result here. I just want the status of the program PSW. So let us say A register is having a value as 12H, register A register. and B register is having say some 24H. So first we need to do the addition, then you can perform the subtraction operation. You need to do add C, okay, and we need to get the status of PSW, and here also we need to get the status of PSW. So this is your work. So hope this is visible now.
So is it add C or add B?
Add C is the instruction. Okay, you
Acha
need
means
to do the add C. You need to use the instruction called as add C for A and B, and you need to get
hmm,
the status of PSW. We are not very much keen on the result here. What is the result of 12 plus 1 2 plus 3 no, 2 4? Okay, we are very much keen about the nature of the result. Okay, so that nature of the result you can say check it from PSW. You have two instructions for addition. Okay, one is ADD, okay, and
hmm,
other is ADDC.
hmm,
Okay, so ADD will just perform the addition between the two operands. ADDC will perform the addition between the two operands along with the carry flag.
hmm.
Okay,
Okay.
so I'll just take some. I'm giving 10 minutes time for you. Okay, so you can after 10 minutes we can just have the interaction. Then once you understand this, then we'll go with logical instructions, and then immediately we'll go to the embedded C. So let me see here. Sir, yeah. I gave a small work to the students. I gave some 10 minutes time so that it can be used as a break also. So instead of continuous 2 hours. Yeah. So I just gave some work. Yeah. Okay, sir. So at 11:05 or 11:10, I'll join, sir. Once get back. Okay, sir. Yes, sir.
Yes, students, are you getting the content? So whatever the task is provided, work on it. Don't left. It is only small task is provided to you. The session will be again get start within a 5 minute. Okay. Yes, what is the response from your side? Are you getting everything properly? Do you understand the content?
Yes, sir.
Nikhil?
Yes, sir.
Okay, whatever the content has been shared on the screen, step by step, definitely it is in a proper flow. And considering your fundamentals, you people definitely going to get sync with them. So I think so going very properly. So if you have any queries, try to put as a message or you can ask. You should interact. It is necessary. If you do not ask the questions, the queries, then how can you get the things? It is not one platform. Everywhere, whenever you are joined for learning anything, there should be some type of interaction from the students. That may be a small question, no problem. It may be a simple question, but it's a query that to be get present. So be proactive. Yes or no? काय कोणालाच काही क्युरी नाही का? जेवढे कनेक्टेड आहेत तेवढे कोणाला तरी क्युरी असेल ना काही कसं करतोय काय आहे कंटेंट कसं करतोय काल किती स्टडी केली हाऊ यू आर गेटिंग कनेक्ट विथ दी बॅकग्राऊंड मटेरियल ॲज अ प्री रिक्विजिट आर यू रेफरिंग सम कंटेंट फ्रॉम एनी पर्टिक्युलर लिंक पोर्टल एनी बुक्स to get proper understand this particular internship content. Nikhil,
Yes, sir.
बाकीच्यांचं काय बोलत नाहीये म्हणजे काय समजायचं next time if I plan something then I will apply the registration fees double of this one and made compulsory because you people are proactively not getting involved I think so. So complete the tasks which have been assigned.
Yes, students, I hope you have completed this job. So anyone can just elaborate this. They can share their screen and they can just explain how what is the result of this and what is the nature of that result. Yes, any student who has finished this work?
Hello, sir.
Yes.
Sir, I am using some online simulator,
Okay, fine.
but sir, when I am simulating, it is
Yes.
given that exception raised add C as an invalid opcode.
Can you share that error to me?
Uh, Sir, actually, I have joined with my mobile phone.
Yeah,
Uh,
fine. You can take a screenshot and you can just share that.
okay,
So,
okay,
what's
sir.
the online tool you have used?
Sir, that is 8051 simulator.varsal app.
Okay, yeah. So, fine, I got it. Right. So, you have used
So
this. What is
just
the
a
program you have
minute.
typed? Because unless we see the program, we can't
Sir,
understand this.
sir, this one, sir.
Yeah, 1 minute. Let me check it.
Yes, sir.
Okay, so here you don't have PSW to check it, first thing,
Huh.
isn't it? So you can't see the check.
Sir, yeah, actually, sir, in the left side here, sir, flags are given
Yeah,
here.
so flags, what
So
is the
by
flag?
combining them,
Yeah, what are the flags
uh,
which are set?
it's a carry flag, auxiliary carry,
Hmm.
user flag, that is the sir,
No, no.
register bank flag. Uh,
Yeah, so which are the flags which are set after execution?
no,
You are
sir,
getting an error.
actually, it is showing here. Yes, sir. Actually, so this error is coming. Exception that add C is an invalid output.
Invalid output. Add
Yes, sir.
ADDC you have used. Okay.
Yes, yes.
Try with ADC.
KDDC.
Just try with ADC. So because some of the
Just,
compilers, okay, some of the assemblers will not support ADDC. Instead, they support ADC.
sir, what I have to write?
ADC instead of ADDC.
ADC.
Yeah, ADC.
ADC A, comma B.
A come up. ADC space A come up.
Yes, sir.
Yeah. Now try to execute it.
No, sir. This is also ADC is an invalid output.
Okay. So ADC is invalid output. That is what it is giving.
Hmm.
Okay.
No, sir. Actually, it is not running. Even if I use the sub
Hmm.
B,
Yes.
A, comma B, then also it is showing the same.
Okay.
So,
So add A comma ADD comma B. Whether it is a valid statement, that you check it.
but sir, let I check if I use add B, then what will happen is let's see whether it is valid. No,
Just
sir.
check
Actually,
with
sir, maybe
ADD A comma B. Okay.
yes,
Just check with ADD A comma B. Right.
yes, A, comma B.
So you are getting it.
Yes, assembling exception raised, add zero, missing one, required positional argument data.
Yeah. So that's why the thing is with the help of this online simulators, right? So they have very limited version of executions.
Yeah.
Okay.
Actually, sir,
So
the thing is that, sir, I have also downloaded the versions
SP.
that you have told yesterday.
Okay.
So this one. And sir, I have extracted the files, but from where I have to install
No need to
this one?
install. Just open that first file.
It's EDCM
Yes,
51DI.
yes. Yeah, you just open that.
Yeah. Then
Okay.
sir,
So there, yeah, I'm unable to check that. Let me see. I'll stop presenting my presentation. Let me see your presentation clearly. Okay. So can you just make it, I think it is in coming in portrait form. Can you make it landscape so that I can see what is the exact thing happening there?
this is this one.
Yeah, this is fine. Okay, so the problem is you don't have JRE in your system.
Actually, sir, this is the downloaded version,
Yeah, fine. So
zip
the
file, and
downloaded
I have
version,
extracted.
yeah, that version, if it has to be executed, you should have a backend of JRE, Java Runtime Environment. You can download that. I will share it now. Okay,
Okay.
okay. So
Hmm.
that first you have to install, and then only you can run this.
Okay, sir. Okay.
So
Thank you,
some
sir.
systems will not come with inbuilt JRE.
Hmm.
Okay, so at that time you have to install the JRE, Java Runtime Environment. Okay,
Hmm.
and then you have to go with it. Okay, so I'm just
Okay, sir.
sharing that link with you.
Hmm. Okay, sir. So may I stop sharing the screen?
Yeah, you can stop sharing. So, dear students, just I'm sharing this link. Those who are unable to execute or do with 8sim51, okay, so first you need to download the JRE environment from the link which is shared in the chat box. Okay, install that and then try to run it. So it will work. Okay, so now let us see the code. Okay, so let us not waste the time. So hope you understood this. Okay, and try to implement this. Okay, ADC, ADDC, okay, all the instructions whatever you have. Now we will have quick review on the other things. Okay, so I'll just share the things. Okay. So hope my screen is visible now. Okay, so the next set of instructions are logical instructions. Okay, so in the logical instructions we have four operations mainly. Okay, so one is AND, the other is OR, XOR, and NOT, that is your NOT operation. So for performing your AND operation, the mnemonic what we need to use is ANL. Okay, and this can be used as we are using your ADD. For performing OR operation, we have ORL, and for performing XOR operation, we have XRL. Okay, and along with this, we have certain operations like clear the register. Okay, so CLR A. Okay, so then CPL A. So CPL is known to be the complement version, that is your NOT gate. Then we have rotate operations. Okay, so rotate operations are the one which performs the rotation of the data within the 8 bits. So rotate left we have, rotate right we have, rotate left with respect to carry, and rotate right with respect to carry. So these are the four rotation operations what we have. Okay, and we have one special case called as swap A. Okay, so now this four things we will see how the things are happening using our, yeah. And in data transfer we have seen your move. Okay, and move C and move X can be used only when you with the real-time hardware. We can't use the simulation version, because simulation version has the memory of internal memory only, not the external memory. Okay. So then we have push and pop for stack operations. Then we have XCHG, okay, A comma Rn. Then we have XCHD with A comma at Rn or Rn, like that. Okay, so now what we see, we'll try to implement this. So without explaining much about this instructions, we will see how they are going to work. Okay, so for this, let us take the basic logical operations. Let us say AND, okay, OR, then we have XOR, and then we have NOT. So first we'll try to implement this 4. Okay, then we use clear. Yeah. Okay, so for this AND, the necessary instruction is ANL, logical AND operations. This is ORL. Okay, this is XRL instruction. This for this we have CPL, and for clear, that is clear. Okay, so now let us take some data. Okay, so let us take the same F0H is one data, and another data, let us take 34H. So let us take these two data and let us see how the data is changed in ANL, ORL, XRL, and CPL. Okay, so we will use R0 register for storing R1 register for storing the AND operation result. For storing OR operation result, we'll take R2. For storing XORL, we'll take R3 register. Then for complement, we'll take R4 register. Okay, we'll take A register only. Then at last we'll clear the A flag. Okay, so this is our task now. So that directly we'll try to implement to understand the basic operations, how they are going to operate. So hope everyone knows about the truth table of AND operation, AND gate, isn't it? So let us say you have 1, 2, 3, 4, 5. So let us say this is A, this is B, so this is X, this is Y data, this is the or XOR. So let us understand the truth table once. 0, 0, 0, 0, 0. So 0, 1, it is 0, 1, 1. So 1, 0, so 0, 1, 1, 1, 1, 1, 1, 0. So this is the truth table. So what you might have learned. Now how these operations are performed. Okay, so whenever you do an operation, okay, so between two numbers, the logical operations, the bitwise representations. Okay, so F0 means 111 0 0 0 is logical AND with, will be performed logically AND with your 3 4, that is 0 0 1 1 0 1 0 0. Okay, so this is the operation what it is performed, and how it is performed, bitwise over the complete byte it will be performed. Means starting from LSB onwards to the MSB, the operations will be performed and we will get the result. Okay, so in this case, if you see for AND operation, okay, so the result should be 1 for AND operation 0 0 1 1 0 0 0 0. So the result is 30H. Okay, for OR operation it will be 1 1 1 1 0 1 0 0. So it will be F4. Okay, then for XRL it should be 1 1 1 1 0 1 0 0. So it will be again, sorry, OR operation XOR. So unlike, yeah, so again for XOR also you get 0 0, and complement of A you will get it as so let us say this is your A register, okay, and this is your B register. Okay, so for A register, if you do the complement, you will get it as 0FH, and once you clear A, it should be 00H. So this should be the data what we should get once we implement the program. So write the program. So move. So I'll use capital S. So move A comma hash 0F0H. Move B comma hash 34H. Okay, now let us perform ANL between A and B. Okay, then move this value to R1 register using A. Okay, so now let us assemble the program. Okay, so your AND result should be how much? 30H. Now let us understand whether we are getting 30H or not. So see your accumulator, it is 30H. We got it. Okay, so in the same fashion, we'll check for OR operation. Okay, then move A comma as 0F0H ORL A comma B, then move this value to R2 register with E. Okay, so run the program. Now see, R0 is 30, R2 is F4, as we have manipulated, as we have done, we got the same result. Okay, so then we'll repeat the same thing for XORL also. So XORL we are keeping, we are moving that value to R3. So we run the program. So C4, I think we did some mistake there. Let me see what has happened. A so XOR 1 or 1 1 1 3 4 only, right? 3 4. So let's see what's happening. XOR Y got it as A comma B. Okay, so sorry, you should be C4 only, right? Exactly. So 1 1 are common, right? So here you will be getting 0 0, right? Now we will see with your complement. Okay, so complement is peculiar thing. So we'll reset. So let CPL A and move this value to say some R4 register comma A, and then clear A. Okay, so assemble, we are assembling it. So sometimes the frequency this will not match. Okay, so it should be very clear. Now see. Yeah, R4. So the XOR value was C4, right? So C4 complement is 0011, okay, and 1011, right? So it is 3B, right? And again, what we are doing, we are clearing the value of A accumulator, which is being cleared. So it seems to be very good, right? So now let us see. We will add something called as swap and understand what happens here. So we are done all the operations. Let it be here. Complement, then swap A, okay. Then we'll do XCHD. We understand this XCH A comma. I'll exchange the data of R0. Then XCHD A comma at R1. Yeah. So we'll assemble this. Now see, swap means the lower nibble and higher nibbles are going to get swapped. Suppose if your value is, say, so here you got it as 3BH. Okay, so first swap A means, suppose if you have a data 34H, after swapping, okay, after perform swapping, you will get 43H. Okay, so your result will be 43H. Okay, so that we'll check it now. And similarly, what happens when XCH is done and XCHD is done? So run stepwise. Okay, so first A is loaded with F0, B is loaded with 34, ANL. Okay, you're moving that value to R1. Then your A is loaded with F0 again, F4, right? So up to here we have C, up to complement. Okay, now see, let us see. So ANL, then ORL. Okay, so now see here, up to here we got it. So complement. Now after swapping, okay, so your complement A, so 3B was there. Now after swapping, let us see what will be the data. It should be B3. See here, the value has been changed to B3. Okay, so swapping means swapping will be done within the operator. The lower nibble will get exchanged with the higher nibble. Okay, then we perform exchange between A and R0. R0 value was B3. Okay, and A value was B8. Okay, next you see XCHD at R1. R1 value is 30. So in 30 we have 02. Okay, so A value was B3. Now let us see what happens with 30. Okay, so see here, 3, earlier it was 0, 2 in 30, and in accumulator we had B3. So now the lower nibbles of the two registers have been exchanged. So swap will perform the exchange of lower nibble to higher nibble, okay, whereas SCH will perform the exchange of the complete 8 bits between R0 and A, whereas XCHD will perform the lower nibble exchanging, okay, between A and B. So before executing this instruction, A was B3 and at R1, so this the 30th location was 02. Okay, so this 02 and B3. Okay, so higher nibble is B for accumulator, and at 30th location it was 0. So the lower nibble at 30 was 3, and for your accumulator it was 3, right? So now this 3 and 2, the lower nibbles alone got exchanged, and now the new value of accumulator was B2, okay, and the new value of your 30 location, which is pointed by R1, is being updated with 0. Now this is how this operations will execute. Okay, so I'll just do this. So let us have for better understanding. Okay, so A is B3, we got it. Okay, and R0 was say some 3, 4. Okay, now once you perform swap A, right, the A value will get updated with 3B. Okay, if you do XCHD between A comma R0, okay, so your A value will become 3, 4. Okay, so now the new value is, again we are taking the same thing. Okay, so the A value will become 3, 4. Okay, and your R0 value will become B3. Okay, now you do the same thing, and if you do XCHD, okay, between A and at R0. Okay, so let us say in 34th location you have a data called as 145H. Okay, so when we do this, the new values of A will be, so B will be as such, the lower nibble will get exchanged with here, so now the new value will be B5, and your new R0 value, or the new value at R 34 location will be 43H. Okay, so see, we have to remember one thing, that XCHD can be used only in your indirect addressing mode, not with your direct addressing mode. Okay, right. I hope this is clear with you now. XCHD, all these operations. Okay, next we have Boolean manipulation instructions. Okay, so to wind up it first. Yeah, and I'm giving some time for you to just check this operations and get back. சொல்லுங்க madam. They are not responding when they send the mails, and now they are telling that it has been dropped.
Who?
A&M, when they dropped the message, see, February 5th they have dropped the message. They have not responded to that mail.
Who?
Those people only. Now they are asking, we have not received the copy. What we can do?
Why this happened, you know? Because of good Lakshmi.
Right?
I am the culprit.
What you complain? What you do?
What I did, na, I gave easy papers. In that, another set of paper is not there.
See, Sir has done straightly, so you cannot include it.
He said I have to take the follow-up. This Vinod.
For Vinod, Vinod also we are given clear instruction that they have paid directly, so they follow-up will be through them only. Those two papers, how it will come into our thing, pa?
நானா போய் சொல்றேன்
நான் ஒன்னும் சொல்லப்பா.
இங்க பாரு இந்த பையப்ல என்ன எழுதிருக்கு பாரு. That one also we have to track. நான் ட்ராக் பண்ணேன். எனக்கு கொடுத்த பேப்பர் தான். அப்ப பேப்பர் லென்த் கூட அது வந்து நம்ம பணமும் கட்டலாதனால அவங்க அந்த பப்ளிகேஷன் ப்ராசஸ் வந்து டிராப்ட்னு மெயில் அனுப்பிட்டாங்களா சாருக்கு. சார் அதுவே ஓகேன்ட்டாரு. அதனால அவருக்கு அந்த பப்ளிகேஷன் வேணான்ட்டாருன்னு நான் சொல்லி முடிச்சிட்டேன். அப்ப இது மாதிரி நிறைய காப்பி ரைட்ஸ் வராம இருக்குமா? அப்ப ஒண்ணுன்னா கேட்பாங்களா? கேட்ட உடனே இவங்க என்ன பண்ணிருப்பாங்க?
See, when they drop the mail, they have to take care of that.
Hey,
and wait,
this is my seafood. My only person is
I'm not telling anything. I already gave more break to them.
enjoy it.
Just 20 minutes. I'll wind up. Yes, students, have you done that? Yeah, so okay, fine. So if you have done the job, then we'll go with the next set of instructions, that is the most important. Okay, so for an embedded engineer, till now we have seen the basics of all the manipulation instructions, all these things, but this is the one which is more important for us. So we call them as Boolean variable manipulations. Okay, so bitwise manipulations we call them as. Okay, so now if you see the bit variable manipulations, I hope my screen is clear to you. So bit manipulation instructions, if you see, okay, so we have the instructions like clear, okay, then clear the bit, then set bit carry, set bit any other bit, then complement the bit and complement carry. These are the instructions. Okay, in the same fashion we can manipulate with respect to the any other operation also. Okay, so with like the like our logical operations, okay, at the same time with the data transfer instructions also. Okay, so the best example we are taking is ANL, and again, so whenever we are doing logical operations or data transfer instructions, it has to be done through your carry. Okay, so like all the 8-bit operations has to be done through accumulator register. Your Boolean manipulations has to be done with respect to carry, means your carry should be somewhere present in the somewhere present in the instruction. Okay, and now here you can see two types of things whenever we are representing the bit, that is ANL C comma bit and ANL C comma forward slash bit. Okay, so now what is this bit and what is this forward slash bit? So forward slash bit will take the will take the address of the location, whereas bit will take the address of the location, whereas forward slash will take the complement of the bit. Okay, then we have the jumping instructions like jump on carry, okay, jump on no carry, okay, and commonly we will make it as jump on bit, jump on no bit, and we have jump on bit relativity, okay, JBC we call it as, okay, jump on the bit, okay, bit comma relativity, right? So next we have the other instructions like other branching instructions like jump, okay, and we have JZ, jump on zero flag, jump on no zero flag, and then we have one instruction called as CJNE, which we call it as compare on jump if not equal to, okay, so compare the two operands, okay, so like A and B, suppose say A and R are not we are keeping, or A and 0 0 we are doing it, okay, so we have first A and the data will be compared. If they are not equal, okay, then it will go to the location called as REL, relative address. If it is equal, then the next instruction can be executed. Okay, so this is CJNE, which is very good instruction. Okay, and there is one more instruction where we have DJ and Z, means two operations are performed in a single instruction. So all the instructions whatever we have seen till now will have only one operation in the single line, whereas this DJ and Z and CJNE are the two instructions which will perform two operations, okay, in a single line, right? So in order to understand that, so again we'll start with a new program. Okay, I'll make it as new. So I'll save this program somewhere, like sample. Right. So now we'll start with bit. Okay. So let us say move a comma hash 0 so 34h. Okay. Now set carry flag. Okay. Then set the bit to 3h. Okay. So now let us see how it will assemble. A simple operation. Okay, so you need to see carry flag. So the carry flag position is this one. So let us see whether it is being set or not, and we'll see where this 23h is being located also in this complete data set. So this is your code memory. So this is your data memory, right? So just stepwise. So accumulator is loaded with 3, and your carry is set to 1. Okay, so your carry is set to 1, and you check your set B 23. Okay, so you have executed set bit 23. So 23. So now somewhere here you will be checking here. Okay, so if you see 00 to 07 is register bank 0, 08 to 0 sorry 08 to 0f is register bank 1, and 10 to 17 is register bank 2. Okay, and 18 to 1f it is register bank 4. Then right from 20, okay, so 20 to 20, so 20 to 2f it is completely your what we say, completely our bit addressable area. Okay, so 16 bits you have. Right from 30 to 7f it is your general purpose area. Okay, so now if you see here in our somewhere here at the 24th location, okay, so 24th location you have a new data which is set as 08. Okay, so to understand this, we have to take the help of bit addressable area of 8051. Okay, so now let us see the bit addressable area of 8051. Right. So now see here. So where is 28 present? Okay, so we have set 23, right? So 23 is present in 24th location. Okay, so this is known to be your bit addressable area. Now see here, from 20 to 27. So from 20 to 2F, your bit addressable locations are there, and all the locations, okay, are addressed as 00, 01, 02, 03, 04. So whenever we do the bit manipulation instructions, okay, so we can use the addresses right from the 00 to 7F, right? So now in our program, we have set the location as 23. Okay, so now let us identify where this 23 is there. So 23 is present here. Okay, so in your 24th byte address, this bit we are going to set. So the corresponding value that should come is 00001000. So this should be 04. Okay, so it is 08. Okay, so it is 24. Okay, so 24, your 4 is being loaded. So now let us step it. Okay, and reset that. And make it as 00. Now assemble it. Now let us see what happens here. So your carry is set. So now see here. So your 0 is 0 location. So where is 00 location? So your 00 location is here. So when it is kept as 1, so all the bits are 0. Okay, and here you are keeping it as 1. So your corresponding data is 01. Okay, so 01 is loaded in 20H. So that is why in 20H 01 is loaded. Now what we do, we try to improvise this. So I'll make it as bit. Okay, now set bit 01. Okay, so now let us assemble this. Right. So now if you see here, bit address is not addressed. Okay, so you can't do anything here. Set bit 00 and 01. So 2 bits I have resetted. 0, C is set. Then first 00 bit is set. Then 01 is set. So 00 and 01 is set. So what happens? So the 2 bits are set here. So that is 00 and 01, 11 it is. Now if you take the complete byte, the byte representation will be 03. So which is reflected in 30H. So 20H. Okay. So this is how we can implement our bit manipulation instructions. Now let us implement that again. Okay. We'll take ANL operation between the carry flag, and now which bit we have to take. So let us say we have to do the AND operation between the 0-second bit. Okay, so if you see the 0-second bit from here, the bit is 0. So 00 was 1. We have set that bit. We have set the first bit, and the second bit was reset. Okay, so it will become 00. So now once we assemble it, okay, so your carry was set. So 002 it was 0. So your carry flag will be reset after execution. 1. Okay, so carry flag is 1. Then you set 2. Fine. And see carry flag status. Now it has been reset. Why? Because your 20 your second bit at the byte location 20 has been reset. Okay. Fine. Okay, so now what we do, we'll just improvise still, and we'll try to implement some logical operations, between the other data set. Now we'll use data transfer instruction. Okay, and reset it. I'll complement the bit, carry bit. So now what we do, we complement the bit, carry flag. So once it is complemented, first it will be cleared and then we are complementing. Complementing will become 1. Okay, so we'll run the program. Right, so running, you got it. Okay, so now we'll move this data, okay, to a bit called 03. Move to bit location 03, comma C. So if you move this, okay, then the value in 20H should be 07. Some small mistake. Yeah, so why it has become chess? Okay. So 03, if you are moving, okay, so 03 is present where? So 03 is present here. So, oh yeah, so it will be B. Okay, so here 1 1 1. Okay, so 1 0 1 1 it will be. So it becomes 6. So it's not 7, sorry. So if you want 7, then the 02nd bit we have to take it. Zero, 2, sorry. Now it will be 7. Okay, so earlier it was set, so that's the reason it became 5. Okay, so we do one thing. Move 02, comma C. Then we are complementing. Now we'll get 7 because the earlier data was there. That's the reason why it has happened. Okay, so this is how we can just do working on the manipulations, data manipulation instructions. Okay, so then we have the peripherals. Okay, so IO ports, everything. This will deal with embedded C. So due to this practical orientation, the time's getting more extended. Okay, just make sure that tomorrow we'll start the embedded C programming exactly. So if any doubts are there still, you can just drop a message here.